about last lectures, homeworks, labs. And while I'm waiting for those questions to come in, Lab 2 will be posted Thursday or Friday of this week. It will be a video, and all the lab groups have been posted. There can be no time conflicts because the lab groups are to self-organize, watch the videos either as a group or watch them individually, but the lab groups self-organize. It should be the group leader who does that, and then get on the schedule for delivering them within 1 week. So, did any questions come in? Well, maybe you're answering them already. The homework problem, this is a real example. What's the maximum rating a road might have to be posted in the United States? Does anybody have an idea?
You say 80,000 pounds?
40 tons, 80,000 pounds, that's right. So 25 tons is not uncommon, but on rural roads, it could be even less. And the real issue is the road isn't the biggest problem. It's typically the bridges and the culverts. So next time you drive over a bridge, you typically see a load rating sign. It's a little square black and white sign right by the bridge. There are so many of them, they're invisible to you now.
Are you recording? Don't say that you're recording.
No. I just put it in the middle. Okay, so good. But these two cameras would have caught it. There. So it's not uncommon where rural bridges are rated for 10 tons. And in the homework problem, you saw a tanker that could weigh up to 25 tons. And with you're familiar with this hydraulic fracturing, one of the first things they have to do, that industry has to do when they move into an area, is upgrade the transportation system. When I was driving in Pennsylvania in 2005, at the height of the hydraulic fracturing and unconventional oil and gas development in that state, subconsciously, I didn't realize it until it came to the forefront. But it seemed like 1 in every 5 vehicles on the road was a truck hauling fluids for hydraulic fracturing, either to the drill sites or away from the drill sites. And you're talking about millions of gallons every day moving up and down the roads. And they start in incredibly rural areas and then move forward. So again, it's not speaking for or against the industry. It's just that not uncommonly, our industry has to be associated with specific resource development strategies. In this case, unconventional gas is a resource development strategy, no different than mining coal or mining trees. Typically, the first thing that has to be done is infrastructure. Okay, so what I wanted to start off with today is where we ended last time, talking about viscosity. And just to forewarn you, next time I see that this, not all classes have this, but this class happens to have a smart tablet. So I'm going to try a PowerPoint next time, just for fun, and you can comment whether you like it or not. And this is what's interesting. I did this class with PowerPoints in 2016, and we were teaching in Merkland. And then it takes me 4 hours to pull together one of those PowerPoints. And then, so one lecture, I didn't have the PowerPoint ready, and I lectured on the blackboard in Merkland. And to a person, all the students preferred me writing on the blackboard over the PowerPoints. Fast forward 4 years to this year, and it may be because of so many students being online, they may prefer the PowerPoint. So I'm going to give it a shot. I'm taking all the suggestions you give me, and I realize that with 96 students, I cannot please everybody all the time. I'm just shooting for the majority, okay? And what's great about last year and this year, no more teaching evaluations because this is all trials. So, you can all tell me that I was horrible and no one's going to listen to you. And, I'm being sarcastic, right? Okay, so yes, give your feedback to the department. Okay, so picking up on what we talked about last time. Viscosity is simply the fluid property that offers resistance to movement. In the contrast to that, you cannot have fluid movements without viscosity. Okay, so we kind of defined it both ways. As we move forward into this class, we'll finish fluid properties, we'll talk about fluid statics. Static means there's no relative movement between particles. After that, we'll move into energy, where things are moving, and we're going to completely relax this and say that we actually have an inviscid fluid, no shear stresses. And that's just to make everything a little simplified to get to the answers we're after, and then we'll add the viscosity back in afterwards. So, with this fluid property, as I introduced last time, there are two fundamental molecular building blocks to viscosity, and those molecular building blocks are intermolecular cohesion and intermolecular momentum exchange, both of which are temperature dependent. And therefore, viscosity is a temperature dependent property. And when you see it in the back of your textbook, you'll see that it is given to you in values for different temperatures. 4 ways of giving viscosity its name. Your book uses dynamic viscosity, and I'll try to be consistent with that in this course. That's what we'll call it here. When you leave here, where you go to work, they may call it coefficient of viscosity, they may call it absolute viscosity, or they may just call it viscosity. All synonyms, they're all the same thing. How to always tell is to look at the dimensions. In a force length time system of units, it's force time per length squared. Pounds second per foot squared, Newton second per meter squared, and of course you recognize the Newton per meter squared as a Pascal, so Pascal seconds. And then, as you'll see in some of the labs or some other industries, for example, in the oil industry, they use something called a poise or a centipoise. So there are other ways of describing these variables, but the units always tell you which one you're looking at about. Because at the end of this lecture, I'm going to give you a different viscosity related to this one, and that's why it's important not to confuse them. So, when we have a fluid, so here's a solid surface. It could just be a horizontal plane. It could be the inside of a pipe, and that's the pipe wall. Okay, it's a solid surface. And that solid surface is not moving. So it has 0 velocity. So just like a pipe, the pipes in the ground that carry the water that you were using this morning, they're not moving, they're just sitting there. But water's moving inside of them. So we're going to have the fluid at some velocity v. And an interesting aspect about fluids when they're near to boundaries. So again, that solid surface is a boundary. It's not the fluid. A boundary could be air. So with the air-water interface at a lake surface, that's a boundary. Yes, the air could be moving, and yes, the water could be moving, but it's a boundary. So typically, we use what's called the no-slip condition. And the no-slip condition has not really been theoretically developed, but it's been empirically measured, meaning that people recognize it happens. And you're going to see that in one of the future labs. You're going to see this. And what the no-slip condition means is that the fluid at a boundary has the velocity of the boundary. The fluid at a boundary has the velocity of the boundary. So, for example, we've got a fluid way up here moving at v. The fluid at the boundary is going to have the velocity of the boundary. So here at the boundary is not moving. It's got a zero velocity. The no-slip condition dictates that the velocity of the fluid here is zero. Somehow, the fluid is increasing in its velocity from 0 to capital V. And later on in the semester, we'll talk about whether it's the straight line, the straight red line dashed, the dashed black line, or the solid black line. So it's possible to have either one of those three and anything in between. Okay? That's the velocity profile or the velocity distribution. We're going to get into that when we talk about the boundary layer later on in this semester. For the purposes of this discussion, we're just going to assume that we have a simple linear velocity profile. Okay? Very simple. So we're using that velocity profile as an introduction to our discussion about shear and viscosity. So there are two fundamental ways particles can move through these fluids. One is that particles are moving in nice, straight, structured lines, or if you're looking at layers, laminae. Okay. In one of the labs, you will establish this. You will use a red dye. When I say you, the TAs did this for you. It's all videotaped. They're still working on the blooper reel. So you'll see how the red dye can stay nice, straight, and structured like this. We'll also be able to calculate when we should have this type of flow versus the other type of flow. The other type of flow is where that fluid particle takes what looks like a very haphazard and random flow direction or path. And yes, it could actually be in a direction contrary to the main flow field. And you actually see this all the time. It just doesn't register in what you're seeing. But I'll point these out as the semester goes along. And this type of a flow is typically referred to as turbulent flow. Okay, and so it's very chaotic. It's challenging to characterize it, and unfortunately, for most engineering applications, that's what we have. So flow in a river, flow in pipes, typically it's turbulent or almost turbulent. Typically where we see laminar flows, in most engineering applications, groundwater flow is typically laminar. Okay. How are we doing for questions online? None? That means I've lost my audience completely by now. So, one of the heavyweights of modern fluid thought, or modern physical property thought, Newton, pondered about this. And what Newton theorized, or what he conceptualized as, if you basically take that same coordinate axis, and all we're looking at is the fact that we have some distance away from a solid surface. That's what y represents, a distance away from a solid surface. And I'm not indicating whether it's in the y dimension, the horizontal dimension, the other horizontal dimension, or the vertical. It's just a dimension away from the surface. And on the other axis, we're going to have the velocity. And as I indicated before, we could have some kind of velocity profile. And again, we'll typically right now just look at it being linear, but in general, let's just draw it as something that's nonlinear. And what Newton hypothesized was just like the dashed red line up above, that instead of looking at an individual particle, you have fluids moving in a lamina, just like a sheet, an infinitesimally thin sheet. And basically, if you had some distance, y1, and another distance, y2, could you ask if they're able to see the red marker okay?
I can see on my computer.
Okay. And this could be the distance between them, either a real finite difference or it could be a differential distance, okay? But there is a difference between those two, and what we would see is, for example, the lower laminae would be moving, obviously, if you look at the velocity profile, at a slower velocity than the velocity at the higher lamina. So this would be, for example, moving at v plus dv. Okay, so again, this is what Newton hypothesized, and what he indicated was that experiment time. You've done this before, right? So when you rub your hands together, two laminae, you generate friction, and therefore you feel the heat. Likewise, there is friction being created between these two laminae. And that friction, Newton perceived as a shearing stress. Okay, so 3, 4. So, if we use the Greek lowercase letter tau to depict the shearing stress, what Newton hypothesized was that the magnitude of that shearing stress was proportional to the velocity gradient. That's simple. So the larger dV between the two laminae, the larger the shear stress. Pretty simply put. And so what Newton wanted to do is, it's hard to do equations when you have that proportional sign. It's easier to do equations when you have an equality sign. So Newton wanted to figure out what that proportionality constant was. And what he did was, he named that proportionality constant that coefficient of the viscosity, or dynamic viscosity. And if you look at the dimensions, shear stress has the dimensions of force per length squared. Okay. And when we multiply shear stress by an area, we get a force. Viscosity has the dimensions, again, of force time per length squared, and velocity, the velocity gradient, dv has the units of length per time, and dy has the units of length. And if you look at all these, the times cancel. That length will cancel with that length, and you're left with force per length squared. Yes?
What does that dV dy represent again?
So Newton hypothesized that the magnitude of the shear force was proportional to the difference between the velocity between the two layers as measured by the gradient. So if you kept dy constant, the larger dv, the greater the shear stress. So his real hypothesis was that shear stress is proportional to the velocity gradient. That's what that's known as. dv dy is the velocity gradient. And it has the dimensions, velocity gradient has the dimensions of 1 over time. So for example, when you calculate dv dy, you could get an answer of, for example, 10 per second, which would be 10 hertz. 1 over second is a hertz. Right? So, A, it's always nice that we have dimensional consistency in our equations. And if you look at what Newton was saying, if this is if we look at dV dy as strain, and this as stress, the viscosity is the slope of this curve. And that's exactly what this equation says. If we bring dV dy to the other side, viscosity is equal to shear stress over dV dy strain. Viscosity is stress over strain. Last time we used a singular stress and strain concept to talk about bulk modulus of elasticity. Okay. Last time at the end of the lecture I talked about wave celerity, the propagation velocity of a disturbance in the medium. How many of you have heard of a Mach number? The Mach number is the velocity of the object or the fluid divided by the wave celerity. So something you've heard about probably for years is related to the bulk modulus of elasticity we talked about last time. Again, in this class, you've experienced almost everything we talk about, everything. The only difference is we're putting equations to it now. And as you move forward into the rest of your junior year or senior year, and then your professional, all you're going to do is take pieces of what comes out of this course, whether you're in structures, geotech, environmental, that's where it's headed. So, dynamic viscosity we can get from the slope of the stress strain diagram. So what I want to do is look at an example problem. You might shoot a chat question to Sam to see if everything's okay in 320. Please.
I think he said it is. Yeah.
Let me draw this. You can certainly copy it, and then we'll describe it. So what you have is a circular sleeve, a collar. And what we're going to do is pass a solid bar through it. And in the annular space, we're going to have a fluid. So in this space, and typically, as you know, whether it's in your car and you use oil or whether it's heavy machinery and you're using grease, this is exactly what's happening in those pieces of machinery. You have two solid pieces of metal moving against each other, and to improve the performance, we put a liquid there that minimizes wear of the solid surfaces, but also allows them to move against each other much easier. So what we're going to do is have this bar moving at some velocity. The sleeve is just fixed in space, and the bar is moving through it. How many of you have not had statics? I know it's a prerequisite for this course, so those people who raised their hand or let me know probably get a pass on this one. But we can draw a free body diagram of the shaft. And we know if we do that, we can then apply one of the laws of motion to that free body diagram. So, here's the shaft. And it's moving at some velocity v, which I'll be giving you the numbers. In order to obtain that movement, we have to push on it with some force, F. So for the free body diagram, here's our force F. And what's resisting that force F is the shear stress operating over the outside of the shaft where it sits in the sleeve. And so we can convert that shear stress into an opposing force by just taking the shear stress itself and multiplying by the shear area. Again, the shear area is the portion of the shaft that's sitting in the sleeve. And question, what's the velocity of the sleeve? 0. Is that steady state or is that unsteady? Unsteady versus steady has everything to do with time. If it's constant in time, it's steady state. If it's not constant in time, it's unsteady. So is this steady or unsteady? Steady. Same with this. That shaft is moving at a velocity v now, tomorrow, next week, Christmas, and at graduation. Steady state. And when we have a steady state system, we can say that the sum of the forces in any component direction, I'm going to select the x as positive to the right.
They're having a hard time reading the red now.
Pardon me?
They're having a hard time reading the red now.
Having a hard time reading the ribbon.
Yes.
So we can say that the sum of the forces would be equal to 0 in the x direction, and this is a steady state. The sum of the forces are also 0 in the y and the z. But the shear stress is not acting in the y, it's not acting in the z. So you could do those analyses, but it doesn't help you address the focus of what we're after, the shear stress in this problem, or the viscosity in this problem, or the velocity. There's one simple equation. You law viscosity, and there's 1, 2, 3, 4 variables. So with one equation and 4 variables, 3 of them have to be dictated for you to solve the equation for the 4th, right? Or you would need to have a different boundary condition. So in this case, sum of the forces are equal to 0, and what that would say, the force pushing the bar is acting in the positive x direction. And the force resisting the movement, the shear force, is acting in the opposite direction. And since they're equal to 0, that would just say that the force on the bar is being offset by the shear force. And that's what keeps this system in a steady state system. Great. So let's put some dimensions.
Okay, we have 2 questions.
Okay.
Does the liquid between the metal and the shaft allow there to be no forces in the Y or the Z? And then fill in to know what's written on the actual shaft itself.
Okay, the first question was about the fluid. And repeat that question, please.
Does the liquid between the metal and the shaft allow there to be no other forces in the Y or the Z?
There would be quote-unquote other forces, so gravity is going to operate, right? And that's probably the only one that would operate. But gravity operates in the z direction, not the x. And again, viscosity in this case is only operating in the x, so we don't care about the x.
And then could you rewrite what is on the shaft itself in a darker color?
And I'll be actually writing that more. We're going to be building on that. So right now I want to give you dimensions. So we're just redrawing the same problem. Why I draw the ends like that is that just means the bar keeps continuing. And this is moving, and we're going to give it a velocity of 0.4 foot per second. and we're pushing on it at 20 pounds. The bar has a diameter of 3 inches. And the angular spacer, which is known as the clearance, all the way around the bar, between the bar and the sleeve, is 0.003 inches. And the very simple question here is find the viscosity. And the answer is, there it is. So find the viscosity. And what we're going to do is apply Newton's law of viscosity in this case in order to make that calculation. So in essence, we know that this problem is asking for the viscosity. So this may be a performance you're trying to design in a system. And what you do now is you're trying to figure out what fluid, what liquid do I need to put in between the shaft and the sleeve to get this performance. Some fluids may give you this performance, others may not. dV would be the difference in velocity from the sleeve to the shaft. If this is moving at 0.4 feet per second, what's the sleeve velocity?
0.
0 is fixed. So you know dV. dy would be the thickness of the angular space. We know dy. Tau, we can get, again, it's not given to us, but we have another condition or equation to help us out. We know from the force equilibrium that the 20 pounds pushing on the bar is equal to the shear stress tau, that's what we're after, times the shear area. What is the shear area? It's that part of the outside of the bar in connection with the sleeve, where the liquid is, where the fluid is. That's the shear area.
You just mean like the circumference?
Pardon me?
You mean the circumference? Or
Well, we'll calculate it from the circumference and the length, but this is an area. So that shear area is over the entire outside, and that would be equal to, can't go any lower. That shear area is the circumference times the length. Okay? So the circumference is either pi d or 2 pi r times the length. Okay, that's the shear area. It's the outside skin of the bar. Okay. The radius, the diameter is 3 inches. Radius is 1.5 inches. And I'd like to work everything in pounds, seconds, and feet. So I'm going to convert that to feet. 1.5 inches over 12 inches per foot. That's R. And then the length, did I ever give that? No. So the length is somewhere in here. I believe 8 inches. Yep, 8 inches. Normally, I'd be using a lot of different colors, but evidently it's hard to see them. Okay, so we have the circumference times the length, 8 inches over 12 inches per foot. And that gives us a shear area of 0.524. And again, for this class, 3-place accuracy is fine. I know you can give me 10-place accuracy. Most of those other places mean nothing in engineering applications. So the next thing is, again, we want to calculate the shear stress, and that's calculated by taking the 20-pound force and dividing it by the shear area. And that gives us a shear of 38.2 pound per foot squared. And more commonly in the class, I will call that PSF, pound per square foot. And not uncommonly, PSI, pound per inch square feet. So we know what the shear stress is. And now all we have to do is apply Newton's law of viscosity to resolve the problem. Like I lost the page of notes. No, you're wrong. So dv dy, the velocity gradient, would be the 0.4 feet per second that the bar is moving at. Minus the velocity of the shaft. Could the shaft move? Absolutely. What might be an analogy in a more realistic system that engineers might work with? Most of you have seen a river, have you not? And many of the natural rivers have sediment on the bottom. The shear stress of the water moving over the sediment determines whether the sediment moves or stays place. If you've armored that system, no matter what the flow, the sediment doesn't move. However, in most western streams or proglacial streams, so in Alaska, streams downstream of a glacier, the sediment is so fine that when the river starts moving, the sediments on the bed start moving. Now you actually have a bed before that was fixed, now it's moving. That changes the shear stress. And the result is, for the same water surface elevation, you could have an order of magnitude more water flowing in that same system. So there are a lot of practical examples to everything we're talking about on just a developmental scale, and that's what we're going to get into in this semester. We're just talking about fluid properties now, we're developing them, and you're going to see them the rest of the semester. So that's dV, and dy we said was 0.003 inches. And again, we want to work everything in feet and seconds and pounds. We'll divide that by 12 inches per foot. And again, I don't know what happened to page 6 of my notes, but it's gone. So maybe on a calculator, I want to say that's about 1,200 per second. 12 times 4 is 0.36. 3 into 36 is 12. I think that's 1,200 per second. Check that for me. And so now that we have not only the shear stress, but we also have dV dy, then we can calculate that the viscosity is equal to the shear stress over dV dy. And that's equal to the 38.2 PSF. Let me separate these a little bit. over dVdy, which is 1,200 per second. Did anybody check that for me?
I got 1,600.
1,600? And then do this calculation too.
That's 0.0238.
So if that's the viscosity you just calculated, what you could do is go to any type of a fluids handbook. Evidently, you have a fluid mechanics book. And in the back, you have this appendix that I asked you to look at. And you'll see that it has some common viscosities, dynamic viscosities, for common fluids. So that's 2.38 times 10 to the minus 2. So that's kind of close to glycerin or linseed oil. That's how they work. Sometimes you could design a problem where you get a viscosity of something that does not exist. And that means you have to go back to the drawing board. You're going to have to redesign that problem. So we talked about, any questions on the example? So we talked about the fact that this is a temperature-dependent property, and typically what you would see is viscosity versus temperature of the viscosity of a liquid. Well, let's look at this first. So here are two different stress strain curves for liquid or fluid 1 and fluid 2. Two different stress strain curves. We know that the slope of either curve is the viscosity, the dynamic viscosity, which has the higher viscosity, fluid 1 or fluid 2. Which slope is steeper? So it'd be fluid 1, right? Has a higher viscosity, more resistance. This more viscosity means it's thicker and thicker and thicker. Less viscosity means it's thin and offers almost no or much less resistance to flow. So if that's true, typically what happens is you would find the viscosity for a liquid typically higher than the viscosity for a gas. And as you increase temperature, typically what you might see is that the viscosity of the liquid decreases and the viscosity of the gas increases. And again, this is typically a log scale, so they're pretty far apart. And again, I explained this last time. For liquids, cohesion, molecular cohesion, is what dominates viscosity. When you heat up that liquid, you break down cohesion. You make the molecules farther apart. It makes cohesion forces smaller. Contrary to that, intermolecular momentum exchange is what dominates viscosity in gases. When you heat that gas up, the particles move faster. You have more intermolecular momentum exchange, more viscosity. Practical example, an airplane. If an airplane is trying to take off on a cold winter day, no problem. Why? Because you have very low viscosity, very little resistance. Move to the summer, and there are some airports today, for example in Arizona, if it's too hot, they can't take off. I've heard, and I've just heard about this, there's something called climate change. And the estimate is that by the end of this century, I won't be around, you may, but by the end of the century, 20 to 30% of the modern airports and modern planes won't be able to take off. So we're probably going to adapt somehow, make longer runways, make smaller planes. But something's got to change, something's got to give, unless we actually decide to do something about climate change. But again, we probably can't reverse that bowling ball that's already in motion. So, related to this, and probably the last thing I'll talk about today, Related to this is another type of viscosity, and it's known as kinematic viscosity. And it is the three-letter lowercase nu. And what happens is, very often in fluid mechanics, when we're theoretically addressing or analyzing problems, the quotient, dynamic viscosity, mu, divided by density, rho, is a very common character. And that's been designated kinematic viscosity. And it has the dimensions of length squared per time. And it's called kinematic because it does not have force or mass units associated with it. That's why. And so the interesting thing is that if you look at what we were just talking about over here, the dynamic viscosity of a liquid is greater than the dynamic viscosity of a gas. However, because of the difference in densities between those two types of fluids, the kinematic viscosity of a liquid is less than the kinematic viscosity of a gas. Because the density of the liquid is so much greater than the density of the gas. Okay, I've got half an hour left. When I set up these Zoom meetings, I usually have the recordings and the Zoom meeting go to 12:15. So they shouldn't cut off at noon exactly. They cut off when I say stop recording. Okay. So, have you ever seen this diagram before? Shear stress on the vertical axis, dV dy on the horizontal axis. And all lecture we've been talking about there just being a linear relationship here between stress and strain. And the slope of that line is the dynamic viscosity. This is known as a Newtonian fluid. Water is a Newtonian fluid, and we'll almost always talk about Newtonian fluids in here. However, is the whole world a Newtonian fluid? Of course not. So anything that deviates from this is a non-Newtonian fluid. So for example, you could have a linear relationship, but you need a certain amount of stress before you get that. That's known as a Bingham plastic. Anybody use a Bingham plastic today? Toothpaste is a Bingham plastic. Now I know something about your personal hygiene. So, we use these fluids all the time, we don't think about it. Ketchup is a Bingham plastic, mustard is a Bingham plastic. You need a certain amount of stress before you actually get the movement. You have another one that looks like this. So, tell me about what's happening to the slope on that one. Is it getting greater or smaller? Smaller. So what's happening to the viscosity, since the viscosity is the slope of the curve? It's decreasing as you get higher and higher. This is known as a stress fluid. Have any of you ever used or are familiar with stress thinning fluids? Do any of you possess stress thinning fluid? Blood is a stress thinning fluid. So I'm sure you're all in possession of it. Asphalts, mayonnaise, some very common fluids we work with all the time. And again, if you have some type of a design problem, this may be an important aspect of it. Geotechnical engineers, mudslides. When you liquefy a sediment, that is a stress-thinning, quote-unquote, fluid. And if you're trying to predict landslides or trying to predict landslide movement, you need the same mechanics we're using, but you need to be able to describe viscosity in this context. And then lastly, come on. Here you have a curve in which the slope is increasing with time. That obviously is stress. The more stress you add, the thicker, the more viscous the fluid gets. Quicksand is a stress thickening fluid. Ethylene glycol is a stress thickening fluid. So I just wanted to bring those to your attention. In this course, we're going to deal specifically with Newtonian fluids. When you leave here in your senior year, you may be using other fluids. And you just have to realize that some of the equations that we develop in here will look a little different because you're using different types of fluids. So that's it for today. Questions? If I get my act together, I'll post the homework for you, I promise. Okay. All right, that's it. Yeah.